It's Matt here. It's a great day for chemistry or physics. All right, friends, I'm sorry I'm not seeing you this day on Monday, but we got to get you ready for your test on Friday. So we need to use this time and move on. You've got one more homework tonight. Day two, we'll check in your homework from the weekend and talk about tonight's homework. Open review if we have time, and then we'll get you ready for the test on Friday. So test is Friday. This discussion right now is going to help you with your homework tonight. It's a little bit tricky. And again, if you need help with the potential field lines, come on in. We can talk about that. Also, we'll go over that on day two. But I think the electric field lines and potential lines problem wasn't too difficult. So I really don't think that'll take the normal amount of time for us to go through. I know sometimes it takes us a long time to go through a problem, but I think we'll be able to crank through those pretty quick. And I'll be posting those keys. So feel free to come in and talk to me about those too. I need to talk to you a little bit about uh, one more type of Gauss problem to kind of get you set up for tonight's homework. We have two more problems for this unit. Nothing on day two, nothing the rest of the week until your test. Okay, so let's get through today. I will be back tomorrow, Tuesday, in case you need to come by and get a little bit of help. Tuesday, Wednesday, I think testum is on Thursday for us. Okay. Here we go. What have we done with Gauss? We have done no charging closed. Super easy. No field, no charging closed, done. We have done all the charging closed, all of Q. Got it. Everything's in there. We have done some of the charge where you've got to create the density, but it is a uniform density. You've just got to create the density relationship. What else have we done? Oh, the density relationship, but it's uniform, but they give it to you. Rho, this density is this. So what do we have left? Well, tonight's homework is going to throw out a problem that says, what if you got this kind of solid object and it's positive, but its density is changing. Its density is going to be R dependent. Let's say B R squared. What does that mean to me? That means the charge density is actually increasing as I move from 0 to R on this thing. As I move from 0 to R, the amount of charge is actually getting more dense. It's like a gas giant in reverse, a planet in reverse. It's like instead of being more dense and becoming less dense, which would be maybe B over R, as the density goes out, this one's actually getting way more dense, right? Okay, so what would I do if I have this relationship? Huh. Well, again, let's start with Gauss's law. What are my challenges with Gauss's law? EDA equals Q enclosed over epsilon naught. Well, this is a spherical thing, so this is still pretty easy. Little r squared. Nothing's changed there, right? Epsilon naught. So clearly the issue is going to be right here. What in the world is Q enclosed? Well, the good news is I don't have any like other object in there that I've got to add in later. It's just this one object. But what the heck do I do with the density? Well, see, the problem is in here, I've got to figure out how much charge is in like a space where R is less than big R. So I'm first going to deal with the field where R is greater than 0, but less than big R. So I'm in there, right? Little r is less than big R. Well, here's kind of the problem. I would love to be able to do, density times volume enclosed. So don't write this down. Don't write this down yet. I would love to be able to do density times volume enclosed, because density generally is charge total over volume total. And to get Q enclosed, I would just multiply that by volume enclosed, right? So like density times the volume enclosed, and I'm good. Like 4/3 pi little r cubed. But here's the problem. There's an R value in my density. So I can't really multiply the boo-boo. Don't multiply like BR squared times 4/3 pi R cubed, because my density is changing. It's not like that's a constant thing at every R. Like this and this This is funky, right? So I cannot do that, although folks still try. So what in the world can I do? What I really need to do for Q enclosed is to integrate density with not volume, but the derivative of volume, right? So like, imagine like, how do I get to the volume of a sphere? How do I get to that? Well, what I do is I take a little shell the size of almost nothing, like nesting dolls, and a shell outside of that, and a shell, and a shell, and a shell, and a shell, and a shell. And all these little shells, right, will eventually give me my volume. So what I really need to do is integrate density because the density is changing. I need to integrate density with the derivative of volume. What is the derivative of volume? It's area dr. So the surface area of each shell inside as I approach my overall volume. So what I'm going to do for these is integrate density, and I'm just going to show you what to do with the cylinder here in just a second. ADR. So now look, I'm going to integrate, and I'm still working on Q and close, right? This is all about Q and close right now, right? I'm just working on Q and close. My density is BR squared. B is a constant, whatever that is. My area is 4 pi r squared and dr. So because it's important for you that you understand the math. What you're trying to do is multiply density times volume. But remember, in this case, the volume of a little piece isn't 4/3 pi r cubed. The volume of a little piece is 4 pi r squared with a little bit of thickness. It's the area of a shell with a little bit of thickness dr, almost like a sheet of paper with a little bit of thickness, right? And so this kind of is my volume. The 4 pi r squared times dr gives me that little bit of volume that I'm looking for. So I can't, I'm not straight up multiplying density times volume, but I'm multiplying in a sense or integrating density with each little volume as my density is changing. Does that kind of make sense? I have seen folks try to do things like, well, can't I just do like BR squared times like integrate this with 4/3 pi r cubed? And the answer is absolutely no. Because what I'm doing now is I'm looking at like every volume added on top of each other, like this volume, all of it, plus this volume, plus this volume. It becomes wildly redundant. I'm adding up more volumes. I want to add up shells. So how do I add up shells? I integrate like this. So now the integration is pretty easy. What are your constants? You've got b, 4 pi. So let's bring 4 pi out. 4 pi b, however you want to write that. The integral of, a little bit messy here, r to the 4th dr. Oh, that's not too crazy. And at this point, I probably should consider some bounds. So if I'm going from like, say, 0 to little r, because remember, I'm looking at Q enclosed, so I don't want to do big R yet. Now, would I do big R? Yeah, when I want to find Q total. Absolutely. Because I don't know Q total rate. It's not like positive Q, but if I want to know Q total, go ahead and integrate all the way to big R. Knock yourself out. So here we go. So 4 pi b. The integral of r to the 4th is r to the 5th over 5. So I get 4/5 pi b r to the 5th from 0 to r. That becomes pretty easy. It's just 4/5 pi br to the 5th. So that's my Q enclosed because it's minus 0, right? So my Q enclosed is 4/5 pi br to the 5th minus 0. If you want to know Q total, just plug in big R there. 4/5 pi b big R to the 5th. Kind of makes sense. But this guy is my Q enclosed. So now I can come back over here. Everything else for Gauss is pretty easy breezy. I got 4/5 pi b little r still, because I'm inside of there. I'm just working the inside. R to the fifth. And then, of course, I'm going to bring over my 4 pi epsilon naught. So E equals R epsilon naught. I've got 4 pi B R to the fifth over 4 times 5 pi R squared epsilon naught. Does this look right? Cancel them, cancel them, cancel them. BR to the third over 5 epsilon naught. At this point, you just kind of have to trust your gut because, like, what does that even mean? But that would be the field. And you can see it's actually related to R cubed. So that's a little bit tricky for us too. But you've got this like R cubed relationship as I go from 0 to eventually big R. Now, if I want to know what it is outside of that sphere, then what I would do is simply plug in big R over here. And when I plug in big R over here, I can go ahead and say, well, what would be the field outside? E would be 4 pi R squared equals 4/5 pi BR to the fifth over epsilon naught. So I get E equals 4. Oh, the 4 pi is going to cancel again, right? BR to the fifth over 4 pi little r squared 5 epsilon naught. And this is where I hope it begins to shape up because, like, I really want this to be a 1 over r squared relationship. This is when I get out to the outside, right? So all I've done is plugged in big R for my little r. And so this goes away, and this is where I really I hope I get a 1 over r squared. This big R is a constant over 5 r squared epsilon naught. So there's that little r squared down there. Cool. Maybe not. What if I had a cylinder? What if I had a cylinder and I was inside the cylinder? So this is a little bit tricky. Like, imagine a cylinder being like all these little like cylindrical shells, right? As I go out. So this should be a little bit tricky. Say my density again we'll say it again is BR squared. We'll just use the same thing. Well, what would I have to integrate? Inside, I would have to integrate density with my derivative of volume, which would be density times area dr. But I got to be really careful with area here. So I'm sorry. I got to be really careful with area. In fact, let me even fix this. Because again, the math has got to make sense. So I don't want to do like pi r squared dr because now I'm kind of getting back to like redundancy. The volume of a cylinder is area times length. Is that okay? So what this really is going to be 2 pi r dr times length. Does that kind of make sense? See, I have to really think about the math sometimes to make sure I'm not making a silly mistake. I'm trying to get the derivative of volume, but again, it's these little like straws, empty straws that are laying on top of each other. The length is a constant thing I can take out, but it's really then to get to like the area, the end of this, the little thickness here of a tube, I would have 2 pi r dr and 2 pi r dr and 2 pi r dr and 2 pi r dr. So really what I want is density times 2 pi r dr L or something along those lines. Does that kind of make sense? If not, we can talk a little bit more about this next week. Okay. So then what do? I simply pull out any kind of constants like density. No, density is not a constant here. Goodness gracious. BR squared, right? So, but the B is B 2 pi L those can all come out. And then what I've got is r squared and r. So I'd have the integral of r cubed dr. And again, the integration is never really the problem here for us. 2 pi bl r to the fourth over 4 from 0 to r. Cool. So then minus 0. So 2 pi bl r to the fourth over 4. So let's just make that over 2. Okay. Hopefully. Then I can use that to plug that into my Gauss's law again. But if you're using a cylinder where it's 2 pi RL. So when I go back to Gauss, E 2 pi RL equals Q enclosed pi BLR to the fourth over 2. And I saw that epsilon not in there. So go bye-bye. Go bye-bye. Go a little bit bye-bye. BR to the third over 4 epsilon naught. Nailed it. So again, I got kind of a weird, funky field going on inside there. Okay. But you can also apply that. You can also substitute in for big R up here and figure out what your overall Q total is if you needed to by subbing in big R for little r in the Q enclosed integration. Okay. That should give you enough to work with tonight. See how you do. Do your best. Don't spend hours on the first or the second problem. At most 30 minutes each, including class time. So watch this video, give it your best shot, and 30 minutes each and be done. Then let's talk on Wednesday. And you can come see me tomorrow if you want, but let's talk on Wednesday and go over it. And then, whatever the questions you might have, I'll be around all afternoon Wednesday in case you still need help. Make sure you're ready to go for the test. I'll be here all afternoon Wednesday during lunch. I'm here for you guys. Okay, sorry I missed you today. See you soon. Love you. Bye.